Right, recording is re-rolling. It's the last minute of the class, so walk around. Help you guys out. You guys been doing a really good job on the slides so far. Let's go over the ideal textbook solution to this. Right, so the first one you did was just pull it horizontally at constant velocity. Set up this free body diagram. You figure out coefficient of friction by, well, you guys took the ratio of pulling force to the weight, but that's the same thing as the friction force over the normal force, which represents the coefficient of friction. Okay. Now, as long as you control for the surfaces, should have gotten approximately the same ratio all the way down. So that when you graph the pulling force in newtons versus the weight also in newtons, right? That's the same thing as friction force compared to the normal force. Right? And then looking at you guys' graphs look pretty well something about like this. About like that, right? Where hey, does this look like y equals mx? Y equals mx, where m is like the slope of this line, right? That's what m is like, is an algebra term, right? Right, slope times x, right? So can you write an equation? And I started it for you. I said F pull, which is the y-axis. So I'm setting up like y equals something, right? Look at that. Or whoops, I don't know why I labeled that m. That's an algebra term, m for slope. But for you guys, what's the physics property that is the slope of this graph? Coefficient of kinetic friction, isn't it? So the coefficient of kinetic friction times the weight, right, is equal to the pulling force. Or you could have said coefficient of kinetic friction times the normal force, right? Wait a minute. Equivalent. Okay. Goodness, oh yeah. Right. What does mu represent? Greek letter mu. There are a couple of valid answers for this one. You could have said coefficient of kinetic friction, because that's what it is. That's the symbol for what it is, right? You also could have said it's just the slope of the graph, right? Pulling force versus weight, right? Which is also true. It's the slope of that graph. Is that right? Okay, you guys get the car? That would have been the first half. Now the second half. This one was a bit more involved. This is where you're like tilting the desk, or maybe somebody had a textbook, you were tilting up the textbook until it broke friction and would slide down at constant velocity. Then you guys were grabbing this angle. And it looked like you guys were getting an angle pretty close to 15 degrees. A lot of you guys are getting 15 degrees, regardless of the weight. You guys had lots of different lab weights, right? Some small, some large, and over and over, you guys are getting about 15 degrees. Okay? Maybe it wasn't exactly that number. You know, maybe it depends on what surfaces you were using. Okay? But suppose that's what you were getting, 15 degrees. And I said take tangent of that angle. What is tangent of 15 degrees? So I'm getting like 0.67. That's what, about 0.27, right? Okay. So tangent of the angle. And then for, oh, whoops. So this graph, tangent theta versus weight. Okay. You should have gotten about the same angle and therefore the same tangent of that angle over and over again. And walking around classroom, a lot of graphs were looking pretty much like that, just like a flat line, like a constant, right? And I started the equation for you guys. Instead of saying y equals, but that's really what this is, right? It says tan theta equals, that's your y-axis. Okay, and it should have just been a constant value. You could have written that number. Actually, that would have been the best answer based on empirical data, just to write that number, right? Maybe you got that number, maybe you got a slightly different number, right? In general, it could represent here. How about this? I need to connect this back to this free body diagram. Right? Remember, I set this free body diagram up for you guys before we started lab, and I said I was going to come back to it and do some more work with it. Right, well, now is that time to deliver on that promise. So let's start with this circled expression right here. The coefficient of kinetic friction is equal to the friction force compared to the normal force. Right? It's just those two divided. Right? Okay, so that's true. Okay. Now let's see, how does that pair up with this free body diagram? Well, I see the friction force is the sine component of the weight. You guys see that? This guy and this guy, same magnitude. So I'm going to substitute that right here. Coefficient of kinetic friction is, right, instead of friction force, I'll say mg times sine of the angle. Okay. And how about the normal force? Hey, isn't that also equivalent to something? It's equal to mg cosine theta. So that's going to go right there. that true? Hey, is something gonna cancel out? What cancels? The lab weight. Yeah, M and G, right? So yeah, not only the lab mass, but you could also take this to different planets and wouldn't affect it either, right? Oh, what is sine divided by cosine? Tangent. That is tangent. Tangent of the. Ah, that's why on this lab paper I had you guys figure out what is tangent of that slide angle, right? You guys see that? Is that all connects together? So u sub k. So the second question: how does tangent theta relate to the say the first side? Oh, all right. So the coefficient of kinetic friction is tangent of the sliding angle. Okay. All right, you guys get that? All right. So once you guys got your lab data, you guys got each of those graphs. Ideally, they should look like this. If you already graphed them and you got something a little different, that's okay. But this is like the textbook answer, ideal textbook answer. You guys got those questions answered at the bottom. Pop that in the gray tray, and then I will get you guys some points. And that is our wrap on today.